So last time that we studied chapter 7, just to quickly review, so we are thinking about the moving beyond linearity. So the most basic statistical model is the y is equal to, the beta 0 plus beta 1x plus epsilon. But we think about the more the general model. So at first we thought about polynomial regression, and we thought about the step functions, and then we thought about the basis functions. That is that we have the function here, but not necessarily the polynomial. And we do regression splines. Regression splines that basically connects the polynomial. Maybe the cubic spline that connects the third degree polynomials, but we assume that this entire function is continuous and also differentiable. Maybe twice. Yeah. And the spline has some knot points, but that is sometimes problem for estimation. So we also discussed smoothing splines. So that means that we have many knot points. And sorry, the knot points, there are several ways to define, but in statistical packages, it's most common that each point is the knot points. So last time I said the knot point between each point, but actually the knot points on observations. So that is the most common way. Then we defined effective degrees of freedom for smoothing spline, because the smoothing spline is more like the choosing the best smoothness parameter lambda. So we define degrees of freedom which corresponds to this parameter lambda. And we discussed it. Then local regression. Local regression is the non-parametric idea, so it's totally different from spline. So the idea is similar to KNN. We choose some proportion of observations to fit the model for locally. So suppose we are given x naught, then we choose, for example, 20% of closest observations to x naught. Then using those observations and corresponding y values, we calculate f hat. That is local regression. And now the 7.7, the generalized additive models. So generally, so 7.7 is different from earlier sections because we have many predictors, x1 to xp. Then, so generally we can think about the y is a function of x1 to xp, the plus error. But this is too demanding, so we have so many possibilities. So multidimensional, so the problem is much difficult. And the one, the most, simple way to model it is just that we assume that we don't have any interaction between x i's, right? So yeah, that's true. Yeah. So yeah, of course, it's not really realistic in some cases, but at least as a starting point, it makes sense that we consider nonlinear function of x1, nonlinear function of x2, but that we don't consider the interaction terms. If you want to include it, of course, you can increase the number of variables, right? So like x1, x2, or maybe square root of x1, x2. I don't know which is better, but then we can consider interaction between x1 and x2. So interaction is, the two variables affect each other. For example, in agricultural example, the fertilizer works if sunlight is not enough, only if sunlight is not enough, or something like that. Or maybe the baseball games, the southpaws, the pitches well against the left-handed batters, or something like that. Yeah, and yeah, so this is the conceptual graph, and so this is one example. And the response variable is wage, and the predictor variable is year. Year is the time point that wage is observed. So generally, the wage is going up over time. So we can have some increasing trend, but you can see maybe in recession, maybe around here, the financial crisis, the wage goes down a little bit. This is pretty rare, but we have the sum function, which is more complicated than a straight line. And age, as discussed, then age 35 to 60, maybe wage is higher. And educational level, this is factor variable. It doesn't specify exactly what this means, but maybe high school dropout, high school graduates, some college education, college graduate, and maybe graduate school. So we have factor variable here. So we can fit this. So yes, so we have to specify the type of F1, F2, and so on. So here, the F1 sounds maybe the spline. Often we use spline for within the GAM, so generalized additive model. And age, probably we do the same thing. And here, I think they use ANOVA. So just one factor variable. Or maybe you can just regard this as ordered variable, and we do polynomial regression, maybe. Yeah, we can even do the smoothing spline, but we only have 5 discrete points. So yeah. And here they use smoothing spline for F1 and F2, and probably F3. I'm not exactly sure from this graph, but maybe they fit the smoothing spline, but just they didn't draw the graph because this is discrete variable, or they just fit ANOVA. I'm not exactly sure. It sounds curve is somewhat smooth, but I'm not exactly sure about specification. But just the point is we have to just specify the type of F1, F2 up to FP. Then you can fit the generalized additive models. And GAMs, GAMs for classification can be done in the same way as polynomial regression. So not the same as polynomial regression. So just if it's not linear, you can just think about the inverse logit function of probability of y is equal to 0 as the function of this. So as long as you use this, then you can do the generalized additive model for binary response variables. Yeah, so that is chapter 7. Yeah, to include more complicated case, the interaction between x1 and x2 or something. Yeah, one way is you include higher order terms like x1, x2, or maybe square root of x1, x2, or x1 squared times x2, or something like that. And another way is to use more complicated, more advanced methods, maybe neural network, maybe support vector machine. Okay, so now we do chapter 7 slides, chapter 7 lab, how to implement the algorithm. I think I have to add some explanation because it only lists code, but I didn't put much explanation. So this is a long PDF file, maybe it's 19-page long, but actually it doesn't include much content, so we can discuss it. Okay, so we use this Nile River data for 7.1 to 7.6. So Nile River has different water level, and the water level is going down, basically. Sorry, some autocorrect feature make it a straight line. But so this has 100 data points, 100 years of Nile River water level data. And we want to fit some line, basically. So that is our objective, and it does not sound straight line. Maybe like this. I don't know. And okay, so linear model. So at least we have some, negative trend. So like this. So we can fit the linear model, and this is the result. And we can get coefficients, and coefficients have standard error, and these are really the statistically significant. So at least the linear trend works. Then next, the polynomial regression. So polynomial regression, that we can use this, the polynomial function, poly time 2. Then we get the first component and the second component. So first component is linear, and the second component is quadratic. And also that these are made so that these two components are orthogonal each other. So to avoid the multicollinearity. And these p-values are both less than 0.001. Maybe this one is about 0.0001, I think. 1. Yeah. So it's small, so we can see both are significant. So probably you have some curvature in this, maybe, and this is positive, and we have to see but this one has the basically x square time, so time square time. So actually we have some convexity like this. And these two components are actually these two. So you can see that this and this may be orthogonal. So if we define just x and x square, x is time, then that these two have pretty high correlation. These two have pretty high correlation. So it has some multicollinearity. So to avoid that, they do some transformation so that these two components are orthogonal. The polynomial with degrees 3, 4, 5, the same thing happens. So we can replicate this by linear model. So if we define just the first column and the second column of this model matrix, then we can replicate the same result. I think these are just the same as above. Yeah, and if you want to put just exactly time and time square, maybe I just write x is equal to time. Then x and x square we want to fit, then we can specify rho is equal to t. Then basically fitted curves are the same, just we transform it. But anyway, we have the coefficient for intercept, coefficient for x, and coefficient for x square. So these look different, but the fitted values are the same. And in this case, x and x square looks like this. I think this is x and this is x square. So time and time square. Maybe no. I think x square shouldn't be a straight line. So I don't know why you put. Oh yeah, but that's true. Yeah. So you can see that it starts with the 1871. So 1871 square and 1970 square don't have much difference. So it looks like they're pretty flat, but still. And x starts at 1871, and this is the 197170. So yeah. So essentially these are this graph, but the x starts at 1871 and ends at 1970. So that's why it looks like this. Yeah, so the same thing is here. So time and the time square. Just remember that we have to put I parentheses to include the square of time as a predictor, because usually this square means yeah, so square. So usually in linear regression, the x times y is not good. Maybe x1 times x2. So this means the three terms, including x1, x2, and x1, x2. So that means the I think the x square, if we put x square, so that means I think the x and x and x square or something like that. So that contradicts the use of this, the multiplication symbol within this LM function. So that's why to distinguish this with this, we have to write I times square. Then we can get the same answer here. So these coefficients are the same as previous one. Yeah, here. And now that we think about the polynomial of higher degree, so polynomial with degree 3, degree 4, degree 5, degree 6, and 7, then we wrote the fitted line. So if we put the lower level functions, we can overwrite these lines conveniently. And actually we have not enough legend, but the straight line is obviously degree 1, I think the degree 1 polynomial. So this is degree 1 polynomial. And the 2, the color 2 is red. So the red one is the red one is right. So the degree 2 quadratic function. And the green one is 3. So green one is degree 3. And so on. So which is the best? I don't know. At least the 2 and 3 and 4 and larger, these are better than others. And yeah, but probably after 2, the difference isn't really large. I think, I don't know, what is color 4? Color 4 maybe, I don't know, blue maybe. Yeah, you can check. And to see which one is the best, maybe we should do cross validation, but it's a little bit complicated. So just the calculated AIC, and the AIC value is minimized at 4. Maybe 7 is also small, but almost at the same level. So maybe we can choose 4. Even 2 is good enough, maybe. And I also did the ANOVA. So we compare the adjacent models and whether LM2 is significantly better than LM1. And these are sequential test results. So second degree polynomial is significantly better than first degree. Third degree, not really. Fourth degree, actually better than 3. And 5, 6 doesn't really improve, and the 7 actually better than 6. I don't really know the 7 is better than 4 or not, but yeah. But at least yeah, I don't know. Yeah, so maybe I should test the second one and the fourth one. So this against this, but this is just one sequential result. Yeah, do you have any questions so far? I think we have already covered polynomial regression. So sorry, I teach many similar courses, so I'm not exactly sure, but the polynomial regression has been done before. And the logistic regression, okay, so just we want to apply the same methodology for logistic regression. So it's a little artificial, but I just set threshold at 1000. Then we make this as 1, this as 0. Then we fit the logistic regression model. So since we have more observations here and maybe few observations here, so at least it's not really linear relationship. Maybe we have the probability Yeah, I don't really know. Maybe linear model works, but I'm not exactly sure. Yeah. So you can fit the y on, sorry, this y. Y is the binary variable. And we fit the first, second, and third degree polynomial and see what happens. And the time has negative coefficient, and this is statistically significant for just the logistic regression with linear term. And if we have two terms, actually it's marginally better, the p-value with p-value 0.096 for the quadratic term. So quadratic term marginally gets the prediction better. If we compare AIC, yeah, actually it's slightly, it slightly gets better. AIC gets worse by 2 if the the predictor is entirely useless. And but it improves the 0.7. So instead of AIC gets worse by 2, it improves by 0.7. So it's kind of, yeah, not too bad. And 3, probably we can imagine it's not significant, and actually it's not. Yeah, we can try 4. 4 gets much better than 2. But from this original plot, probably, if we reduce the information into binary, the 0, 1, probably we don't have much indication that this is, yeah, this is the more complicated than quadratic curve. Maybe this is just linear. So the probability of 1 is just fitted by logistic regression, or maybe this one and this one, maybe more steep curve may be possible, like I don't know. So if this curve is not really logistic, then maybe quadratic term works better, but yeah, I don't know. Yeah, but the linear term or maybe quadratic term, that sounds sufficient. If you wanna explore more higher degree polynomial, then you can do that. Any questions so far? And generally, it's difficult to find examples that polynomial regression works good. So I mean, independent data set, that is true. So dependent data set, of course, we have some pattern, so it's possible. But the independent data set, it's pretty hard to find the example on which the polynomial regression works. The last time I discussed the number of the age of baseball players against the number of home runs. In that example, observations are players, so those are independent. And even though we have some, the concave curve, we have some peak age of baseball players, but still it did not work when my student tried it. So logistic regression, I think even it's harder to make it work. Maybe the quadratic regression still works, but the cubic or more, probably it's pretty hopeless. Yeah, so dependent data is different. So we have some, the momentum if the time series data, but otherwise it's hard. So next one is step functions. So step functions, okay, so remember that the idea is we have X value and Y value, and then we have, so suppose this kind of data, then we fit just the step functions here, right? And one problem is how to set the not point. But we split this data so that the observations are separated into the same the groups which have the same size. So in this case, if we have 300 observations, 100, 100, 100. So this is one way. And that can be done by this cut function. So cut function basically create the several, in this case, four categorical variable. For category, what should I say? So create a categorical variable with 4 levels. And 4 levels have equal number of observations. So in this case, the threshold is 1.9, so 1,900, and I think the 25 observations each. So 1925 and 1950. So those are thresholds. So we have 25% observations each, and we created basically 4 categories. So this is 1871 to, actually to, sorry, maybe 18712, I think the 189695, right? So it's not really 1900, sorry. So this is, I think, the 1896 to 1910. Sorry, 20, sorry. I'm not that good, not good at addition. Okay, so, and this is 1921 to 1945 and 1946 to 1970. So we make the 4 categorical variables, which corresponds to each, the step function. So using this cut function, that you can use the you can do step functions. The format is here. So LM Y on cut time 2. So here 2 actually. So we only have the 2 periods. Yeah, and so this automatically determines the knot points. So knot points are not optimized, but we just try to fit the regression with different number of knots. So number of knots from 2 to 10. So we do this for I is equal to 2 to 10. Then we calculate AIC and we plot. And what happens? Also, I make a plot and the fitted function. And this is the result. So the red one, you can see that these have the 1 knot. And the green one, we have 3 levels. So this has the 2 knots. And the blue one, we have the 3 knot. So which is the best? It's not clear, but of course the fit is better if we have more levels. Maybe blue one. If we see blue one, actually, yeah, it makes some sense. So this period, first 25 years, actually level is higher. And next 25 and the third 25 years and the fourth 25 years, almost at the same level. Yeah, actually, if we see this, actually this range, the water level is slightly higher, I think. So it makes some sense, but you can see that these 3 levels that don't differ each other much. So we can calculate AIC, which is the best, and you can see these AICs. So that means actually the last one, the 3 knots, is better than 2 knots or 1 knot. Maybe just because we want to separate the first 25 years. If we have only 1 knot and the just first 25 years and the last 75 years, then maybe it works better. But this is a kind of ad hoc model because we handpicked the threshold. And yeah, actually, I investigated AIC for the 1, 2, 3. 1 is just, I think this is with only intercept. So this is 1 knot and 2 knot, 3 knot, 4 knot, 5 knot, 6 knot, 7 knot, 8 knot, 9 knot. I think that's the case. Yeah. Yeah. So cut time 2 means we only have 1 knot. Cut time 4 has 3 knots. So cut time 10 has 9 knots. So 9. So this is 9 knots. 10 minus 1. So which is the best? Probably 4. Yeah. But if we optimize the knot points, so this is ad hoc optimization of knot, ad hoc choice for knots, then actually the prediction performance gets better. And actually I make these 4-step functions, and actually AIC gets much smaller, 1251. That is 20 smaller than this, even though we have the same number of knots. And this is statistically not valid because it's ad hoc. Maybe we can set up some criterion on even if the selection of the choice of knots are arbitrary, still that we can compare it with just automatic the knot points model. But in a naive sense, this is statistically not valid. And what I did is simple. You can see that this sounds outlier, right? And in the last 75 years, level doesn't change much. So I try to fit this level, this level, and also this level, and just I single out this observation and this level. Then actually the AIC improved. So it's a kind of just based on one outlier. So just I single out the this outlier. So I use one parameter for this outlier. So this is very ad hoc choice, but actually the AIC gets better. So I don't know. The people do that in practice, right? So this is an outlier, so we exclude it and we look for a better model. Yeah, so yes. Yeah, when cross-validation or something similar to cross-validation training test approach can be taken, then of course you can also optimize the choice of thresholds. Yeah, so this is what I fit. Do you have any questions? So in short, step functions are not difficult. Step regression is not difficult to fit because step regression is just using the one factor variable. So, and each level of the factor is just certain interval. So not very specific function we have. We use the just cut function there, but basically we can define any function. Yeah. And the next one is the basis functions. I just misspelled it as basic, but the basis function. And here I try to use the cosine and the sine curve. So first two variables are just the cosine and the sine curve with period equal to 200. So here, the number of observation is 100, remember. And also we use the cosine and sine curves with period equal to 100. So the black and the red curves have the period of 200. You can see that over 100 years that we only have just a half period. And the blue one and the green one are both the trigonometric functions with period equal to 100. But this is, the mean value is 0 for this function, and also the the maximum is 1 and the minimum is 1. So that does not capture this range. So just I artificially add some values. So I multiply 300 and add the mean Nile River level. Then I just overlay original observations and these 4 curves. So these 4 curves, the level of these 4 curves is just artificially determined. I mean, maybe the magnitude and level are artificially determined. just to see the idea of this regression. Yeah, so here again, yeah, actually the color for is blue, yeah. So black, red, green, and blue. And again, we can just use usual linear regression. AIC 1274. This is almost the same as AIC for step function. So we use the 4 components. So this smooth curve and step function work, at the same level of fit. So I don't know which is better, but yeah, this makes sense. Possibly, the trigonometric function, we can extend this for extrapolate, but anyway. Yeah, it makes some sense. It captures the curve. I think around here, it's pretty questionable. So usually we fit both ends are not questionable. Often the both ends are questionable. I mean, here it looks fine, but I don't know, this goes down, right? So it's correct or not. So usually they're both on both sides, the fitted curves are not reliable. And next one, regression spline. This is more non-trivial one, but still it's kind of similar. So basis, the spline, basically we need the knot points, right? We have the knots, maybe C1, C2, C3. Then after that, we fit the curve, right? So that we fit the cubic curve here, usually if the cubic spline. Then we have one more parameters to adjust the shape, then one more parameters to adjust the shape, then one more parameter here, right? So as long as we can define basis, then we can fit the model. So instead, in addition to intercept, we have the 3 components here, and we have one additional component here, here, and here. So as long as we have these 6 variables in addition to intercept, then that should be fine. And this BS function, basis spline function, can create this, the 6 variables. And here, knots should be specified, pre-specified. So I choose just these 3 points. Thus, these are just splits the entire data set into 4 equal parts. Maybe I should say 1896.5. Yeah, 95.5. Yeah, but yeah, do this. So once you get the basis, you can fit with just linear model. AIC 1277. It's just slightly worse than the other, step function and the basis function in this specific example. Yeah, and alternate way is the BS, the time, the DF is equal to 6. So this 6 is so-called DF, but actually the 6 is the degrees of freedom minus intercept. When we fit the linear model in R, usually we don't specifically put intercept. Intercept is included in default. So they probably want to make this number as the number of columns for the model matrix, excluding intercept. So to be specific, this one. So we specify 6 rather than 7. And yeah, we can use the predict function to get it. I use predict function to get the standard error. So in this case, so this is original scatter plot, and this is the fitted curve. I think this is redundant. That's the same thing. So fitted curve. And so these are confidence band. So confidence band means the band for the fitted line. So not for observations. So this is 95% confidence interval. So that means this estimated curve may not be the true one, but with 95% confidence, this curve is within this band. And you can see that this band is wider at the both ends, basically indicating the estimated curve is not reliable at both ends. That is basically what I mentioned a few minutes ago. Fitted curve. Great. Yeah, so that's it. Yeah, and another way is to use this NS function. NS and the BS are similar. And what's the difference? So NS is orthogonal basis. So if we use NS, we have very similar matrix, just the 100 by 6 matrix. But you can see if we see components, these components are here. So first component is black one, second one, red one, and these are orthogonal each other. So the spline, basically we have the 3-degree polynomial first, x and x squared and x cubed. Then we add x minus c1 cube plus and x minus c2 cube plus. That is original construction. But these have, some correlation. These variables have some multi-collinearity. So this uses orthogonal basis. So maybe this NS has less problem about estimation. So multi-collinearity is severe, then sometimes we go to the non-singular results and we have some error. Any questions for 7.4? Yeah. Then next one is smoothing spline. So remember that the smoothing spline, the minimize is the RSS plus the lambda times the range, the minimum to maximum, and the estimated curve, the double prime dx. And we have to specify lambda, but we have the so-called effective degrees of freedom. So equivalent number of parameters. So large lambda makes very smooth curve. So that is very less flexible. So if lambda is infinity, basically the very smooth curve is only allowed. So that means that we make a straight line. So lambda corresponds to effective degrees of freedom. And it sounds in our spline, smooth dot spline function. Actually, the df is the more popular parameter to specify. So this is effective degrees of freedom we specify. And actually, there is a rule that the df is larger than 1. So df is equal to 1. I think it should be possible to fit the straight line, but actually it does not work. I don't know, some coding reasons there. So 2 or larger works fine. So we can fit 2 or 4 or 6 or 8. Of course, we can fit the df is equal to 7.5, for example. Can be any number. Any number larger than 1. And also we can use the optimal degrees of freedom by specifying CV is equal to true. Then actually when we optimize this, the degrees of freedom is equal to 23.45 is the best. So actually it's pretty high degree. And those are fitted curve. Yes, so 1, 2, 3. Oh, it sounds strange. Yeah, it sounds a little strange. So these are fitted curves. So the light blue one DF effective degrees of freedom is 23, and this is best. Okay, so but it does not look best in our view. Yeah, so this is kind of the difficult part for dealing with dependent data. So it sounds like the green one or blue one looks much better than the light blue one. Light blue one is too noisy, too bumpy. But statistically speaking, it sounds that this one is the best. I think 1, 2, 3, 4, 5. 4 is blue, so 5 is light blue. So yeah, so that is the statistical result. Yeah. At least, you know, the light blue one captures that around these observations, maybe these observations, and these small bumps and these bumps. So yeah, statistically it may be better, but that is assuming that assumes the data are independent. So these two observations happened by chance, but actually probably not. So these two are related, the atmospheric events. So probably this isn't appropriate, but assuming all observations are independent, this one is the best. Sorry, I spent so much time, but the local regression, we use totally different function, the lowest function. Yeah, I forgot which package, but you can see the earlier slides to see which package include this. Or you can just search for this function on the internet, then you can see which package this function is in. And the lowest function, yeah, the format is very similar to LM, but we have to specify how many percentage of observations are used. And also it uses weight, and weight is determined by probably normal density function, but you can probably change that also if you specify option. And this is so-called S in the slides. So 20% of observations are used. For regression. And this number is small, the more noisy, bumpy curves. And this number is larger, then it's much smoother. So this one is very smooth, should be very smooth. And actually, you can see this one, this corresponds to S is equal to 0.8, and this is the very smooth. And the black one, I think this is 0.2, less smooth. Yeah, so that is 7.6. Sorry, I don't have enough time, but still 18 minutes. So maybe I split the section to discuss the exercise. Yeah, exercise is entirely almost the same as almost similar to the lab slides. So fitting splines on Boston dataset. Boston datasets, remember that we have 506 observations, and each line represents town in the suburb of Boston. And here our objective is to explain the distance. So we explain NOx level, so the contamination, the environmental variable by the distance from the city center or something like that, industrial center. So we split the data set into training and a test, then we do regression. So this is the way to define training and a test set. So just I want to make sure that everyone gets the same answer. So just you define the data set, training set and test set with this code, then do regression. So the step function and the basis spline and so on. Sorry, I think I should explain this in a shorter time period, but I will make the 2 breakout rooms you to discuss. And I think, yeah, I think it's good number. So you can discuss there from now on. So I make 2 rooms, 3 students each, maybe 10 minutes.
Are you all back? We were
Sorry, I'm muted. Sorry. So
we were wondering what happened.
So I distribute solutions today, and you will have more exercises in the future. So yeah, you can spend more time to discuss with classmates. Yep.
Could you give?
Yep.
Sorry.
Go ahead.
Could you give us a little opinion on how you wanted to do? Or you're going to give us a solution, so we'll know that.
RSS,
but your preference on RSS, yeah, that was what the big.
Yeah, actually, I calculate it by hand. I mean, I use its fitted value and take the difference between actual and fitted value, then take square and the summation. Yeah.
All right, thank you.
Yeah. So see you after the spring break.
All right, take care.
Take care.